Alright, welcome to some new slides. These ones are about a concept called sets, which are kind of like the thing that underlies most of mathematics. So you can define everything in terms of sets. It's really cool. And it was invented by this dude named Georg Cantor. And his goal, again, was that with this thing called sets, let's take those and somehow define every piece of mathematics with them. And honestly, it worked out. So he just wanted everybody to have like a common language to talk to each other with as they were doing math, and it really did work out. So it's super cool, and let's learn about them. So what in the world are sets? It's a very, very generic idea, and that's how it like generalizes to a bunch of different kinds of mathematics. So let's talk about all that. So let me fix my pens. Alright, so yeah, just a set by itself, it's a collection of objects. It's just a bunch of stuff, okay? That's really all it is. And those objects can legitimately be anything, alright? Like, you can do math by putting a set of, or you can create a set of like every green M&M in the universe. Like, that is a potential set that you could create. It's that generic. You could consider it, okay? So that's very odd, okay? So you can make a set of green M&Ms if you want. You can make a set of numbers if you want. And the things that you put inside are called elements, so every set is made up of a bunch of elements, potentially infinitely many. And then the easiest way to describe your set and what's inside of it is by using this roster notation. And so that's when you just like say that this set holds these things and here are the things. Like you're giving like a roster as you're calling attendance for your set. So like here is a set called A, and we can define it to hold 1 and 2 and 3. Okay, so like a set is just like you give it a name and you say what's inside, and it's curly braces that denote a set. So it's like you put a bunch of stuff, commas separate it, and like that's it. Alright, so C's elements go here. That's how you describe a set using roster notation. So there's the A set, and then like here's the B set. You can say that, alright, B is the set that holds 2, 4, 6, and 8. So you can just pretend that that is just like a bag, and it holds on to those things. Okay. One big thing though about sets is that every element inside is unique. So you can't like if you repeat stuff into a set, like you try to add a bunch of 2's into a set, it's really not going to do anything. So like this set with a bunch of 2's is the same as this set because like you chop off any duplicates. So that's sets in a nutshell. It's just a bunch of stuff. It's a collection of objects, and those objects are called elements. Okay. Of course, there's a ton of notation every time you learn a new thing. So those elements, you have a piece of syntax for saying like something's an element of a certain set. So it looks like this. So if A is this set, 1, 2, 3. So let me draw A over here. So like here's A, the set. It holds 1 and 2 and 3 somehow. The order doesn't matter as well in sets. Order doesn't matter, and then duplicates don't matter. Well, what we can say that 1 is in this set, like we know it's there, very quickly by saying this syntax. You say 1, and this is like the Greek epsilon, I think. 1 is in A, okay? So you say that symbol just means in, okay? It's like an E, it's like the Greek E, and so it really means like 1 is an element of A, but I'll just read it as in. 1 is in the set A, okay? So that's a true statement. 2 is also in the set A, 3 is also in the set A, and 4 is not in the set A, so you can just draw it with a slash, like 4 is not in A, okay? So you can read it like that, or alternatively it's like not an element of. Oop. So not in, which makes sense, okay? So there's that. 4 is over here. It's not in the set A. Could be in some other set, but it's not in A. We also have the empty set. You can consider the set without anything inside of it, and you can write that with 2 curly braces right next to each other. Or another option is like a little O with a slash through it. It's like nothingness, the void. It's like if B, we define B to be the empty set, then it's just like a set with nothing in it. Okay, so there's that. Some sets are finite, some sets are infinite. So like a finite set is either empty, of course, or its elements, you can number them. You can be like, you can pick some ordering for them, and there's like a largest number for the thing. All right, so let's just try to say that you can enumerate them, you can list them out, and you eventually stop if it's finite. When it's infinite, you cannot stop. You have so many elements, like you can have a set of every number ever, And of course that never ends, right? So like you can consider the set of all the positive numbers, 1, 2, 3, 4, ... and that you're never gonna finish listing those. Okay, so that's an infinite set. And then for finite sets, you can talk about the cardinality. You can talk about how many things are in that set. So this is just a pretentious way of saying how big is the set. The size, cardinality, and size are synonyms. So the number of elements in a finite set, you denote it like this. You say like absolute value symbol, and that tells you how big the set is. So like the cardinality of this set A with 3 things is 3. Okay, so you put those bars on the side. Now you're talking about the size of the set. Okay, there are a lot of sets that we use a whole lot, just like the positive numbers, for example. So we give them special names so we don't have to list them out all the time. So here are 2 special sets. N, for example, stands for the set of natural numbers. All right, so it's every integer greater than or equal to 0. It's this set. Start with 0. This is N, the natural numbers. 0, 1, 2, all the way on and on forever. In some math classes, this is like a war going on between the computer scientists and the mathematicians. So some mathematicians think that the natural numbers start with 1, but they are wrong. We're going to say in this class that the natural numbers start at 0, and we're going to be correct, okay? But honestly, you'll have to ask. Sometimes somebody says that natural numbers and they mean they start at 1, but honestly, it's not a big deal. But we're going to consider them starting at 0 in this class. And this little font, by the way, the style of writing a word, writing a letter, like if I did it like this, that's how you'd write it with just your handwriting. It's called blackboard bold. Okay, so really this N, like I guess in slides I could have made it like this. It's supposed to be this. It's supposed to be like a filled in bold version of N. That's the natural numbers set. That's what it's really supposed to look like. But like every teacher ever didn't want to like fill in the letter N all the time, and so they came up with a new way of writing it just to make it look kind of bold on like the blackboard or the whiteboard, I guess now. So it's really supposed to be this one, but nobody wanted to color in that, and so they invented this kind of font. It's called blackboard bold. Okay, so I'll probably write it like this, but in your book you're going to see bold N, and that means the natural numbers. All right. Z is another big one. Again, blackboard bold, so you don't have to fill it in. That's how I'll write it. That's the set of every integer ever. So it's like all the negative integers, 0, and all the positive integers. So N is in Z in a certain way. We'll talk about that. But like that's every integer, and the reason it's called Z, like N makes sense. Natural numbers. That's N words. Z, there's no Z word for integer, right? So it comes from German. It means Zahlen, and that just means numbers, so that works. And then if you wanted the set of all the positive integers, and you're like me and you think that the natural numbers start at 0, you say Z with a plus sign as a superscript, and that stands for all the positive elements of the original Z set. It's the other set that's just the positive integers, okay? So that is the sets N and Z, natural numbers and the integers. There's a couple more. Let's talk about them. We got Q and R. So Q is a set of every rational number, all right? So it's a little bigger than the integers in a certain sense. It's still infinite, of course. And that's the set of every ratio of numbers, every quotient, okay? So that's the idea. And you can define it using smaller sets. So Q is a set of every element that looks like A or B, where A and B are integers, right? They're in Z, see that? And then B is not 0. Okay, so Q stands for quotient, of course, and so all these numbers, you can write them as fractions, and so it works out. Every integer, of course, you can write as a fraction too. And so this is Q, and there's a whole lot more where that came from, of course. Okay, so that's that one. And then finally, like the biggest set of all the numbers that we care about in this class is the real numbers, R. R for the real numbers. It's excuse me, it's Q, it's all the rational numbers, and then as well as that, in addition, it's the set of all the irrational numbers too. Okay, so it's all the rational numbers as well as the irrational numbers. So like it's all these guys plus like a pi plus like a square root of 2, all those numbers that are irrational. The real numbers has it all. Okay, so that is what R is like. It's just like all the generic numbers that aren't imaginary, at least. And so, yeah, your book is going to use bold for all of them, and I will try to give you a taste of blackboard bold as well, because you'll see that in the future. It's like your book says this in bold, but I'll write it like this. Blackboard bold. N, Z, Q. It's very satisfying, though, writing it like this. And there's R. Okay, so those are pretty much the sets that you'll have to remember, or just go back and look them up. So, of course, we're not done with notation. There's so much to set theory, sadly. So we have even more notation to talk about. I'm sorry, but we're almost done. There's other ways to talk about like what's inside of a set. All right, so let's talk about set builder notation, because that brings like logic, predicates plus sets together. So set builder notation is when like you have a starter set and you want to make a smaller version of it. You want to like pick some certain things out, and you'll pick those things out using a predicate. So this is called set builder notation. So this is like define A to be the set where you take all the elements of some other set S. Think about those, like where X is in X, or X is in S, and you read this little line, this little colon, as like given or such that. Some people also write little pipe characters instead of the colon. Either one works. So it's like take all the X's in S and filter them out such that P of X is true for them. Only take the X's in S such that P of X is true. Right? So I'll read it like this. The set of all the X's in S such that P of X is true for them. So like the predicate is picking out those elements of the bigger set, and you're making a smaller set A. Okay? And that pipe character is the same as the colon. So it's like, all right, B, define B to be the set of all the integers such that, the set of all X's in the integers such that X was even. So that's a predicate, of course, right? So this defines B to be all the even integers. Do you see that? That's pretty nice. Let's see. There's also a concept of a universal set, and this one won't make a lot of sense right now. We'll get there, though. So there's a universal set U that is implied. Unfortunately, it's always implied. It's in, it's just like, it has to do with what you're mentioning. So it's the set that contains all the elements that you're mentioning in some kind of context, which is very, very vague. So like, if you're talking about a bunch of different like sets containing integers, your universal set, like the thing you're talking about, is probably the integers, just like the whole set of integers. But like, there's always a context involved. And we'll talk about that later, okay? So this one's a bit generic. We'll get to it, I promise. It'll make more sense then. And then finally, you've actually learned a lot of set theory before as a child. We teach Venn diagrams in elementary school and onward, right? And those are just drawing versions of sets. Like, all right, you've made little versions of these before. Like, all right, let's define the set A being 1, 2, and 3, and like B being the set 2, 3, and 4, and do you see what they share? Venn diagrams totally are representations of sets. So like if this is A is 1, 2, 3, B is 2, 3, 4, you can draw them like this to make it very clear what they have in common. Okay? So that's nice. That you already know. So that's cool. Let's see here. Almost there, and then I have some questions. We can use all this notation, but we have to build it up. There's a lot of it, all right? Let's talk about subsets and supersets. So, like I said, Z is like bigger, right? It's still infinite, but it's bigger than N, right? Because N it lives within Z, right? So there's a concept for that. There's like, you call it a subset. So A is a subset of B, if and only if, you define it to be, A is a subset of B if and only if, for all X's, for all elements X, if X is in A, then it must also be in B. You see how it's like implying that like B is the bigger thing? A is a subset of B, it's smaller. If X was in A, then it's also totally in B. See how I'm reading that? For all X, if X is in A, then it is in B as well. So that's how you know it's bigger. So this is a subset, for example. Like you got, how do I want to do this? Like, here's these two. Let me draw these two examples real quick. So A, it'll give away an answer too. So here's A, it's 1, 2, 3. And like here's B. It's all those as well as 4, 5. So do you see how A is a subset of B? That's the idea. So every element of A is also an element of B. That's how you can think about it. But this definition, it's a little, let's see, what's the word? It's a little forgiving, I would say. Like, it's okay, it doesn't have to be strictly smaller. Like, if A is equal to B, if they're the same set, A is still a subset. Does that make sense? Like, this is still true. Like, every element is still an element of B. Also, if A is the empty set, Like, are all the elements of A also elements of B? Like, if A is the empty set, it's always a subset of everything. See that? It's like, all right, if X is in A, then it's in B, and like, this is always false, right? Because it's empty. There's nothing in A, and so that just makes the implication always true. So these, we call them, they like vacuously satisfy the definition. That's the fancy word, vacuously. But usually it's like it's strictly smaller. You think of it that way. But here is the notation for subset. A is a subset of B. This is how we rate it. Right? This is the subset symbol. And you see how it looks a whole lot like a less than or equal to sign, which makes a whole lot of sense for these ideas and this idea. It's like it's a smaller set in theory, right? Assuming it's finite. So this is the notation for subset. It makes a lot of sense. Like, this is the smaller thing, B is the bigger thing, A has all the elements of B. Okay? If you don't want the equals part, you call it a proper subset. You say that A is a proper subset of B if and only if, like, every element of A is also an element of B, and A is not equal to B. And so that's strictly less than, right? This one. You see that? And the similarity between that and that. So you write it like this if you want a proper subset. See that similarity there? That's pretty nice. So that's similar ideas, which is not too horrible. And then superset is just the flip side, just like greater than or equal to. So A is a superset of B if and only if B is a subset of A. Okay, it's just the other way of thinking about it. And so you write it like this: A is a superset of B. It's just this, like, it's just the other way reversed, right? B is a subset of A. See that? And you totally know what proper superset means as well. Okay, so here's a bunch of sets, A, B, and C. A is equal to C, by the way, but they're separate sets still. And let's talk about all these ideas. All right, so A, first of all, A is a subset of B. It's smaller. It's technically also a proper subset of B. All right, we'll get there. A is a subset of C. Are all the elements, like all the elements of A, they exist in C. It satisfies the definition. The empty set is a subset of A. Because, like, all right, is every element in the empty set also an element of A? Sure. There's nothing in the empty subset, or in the empty set. It is always a subset. A is a proper subset of B, for sure, because all the elements of A are in B, and then B is also bigger. A is not equal to B. Okay? The empty set is a proper subset of B, which makes sense, right? Because, all right, all the elements of the empty set are in B. There are none. And then empty set is not equal to B. B is bigger than that. Okay? The cardinality is larger. A is not a proper subset of C. See, I can write it like that. That's totally fine. Draw a little slash. A is not a proper subset of C because they're equal. One's not bigger than the other. C is a superset of A. That's totally fine because A is a subset of C. Right? You just think about it the other way if you want to. They got all the elements. It's okay for it to be equal because it's like the greater than or equal to sign, and we got the equal to part right now. And then B, you just like flip it. A is a proper subset of B, and B is a proper superset of A because it's strictly bigger. Strictly bigger, and A, like, it contains all the things that A contains. All right? So that's that. And that's subset and superset. And notice that, like, if it's a subset, it could be equal. If it's a superset, it could be equal. You can actually use that idea to prove that sets are equal. All right. So let A and B be sets. A is equal to B, and only when this is true, right? Does this make sense? A is a subset of B, and B is a subset of A. You see how the only way that both of these could be true at the same time is if they're equal to each other. Like, all the elements of A are in B, and all the elements of B are in A. That implies a whole lot. Okay. So let's expand those definitions. Like, we have these. Let's think about it this way, because we can prove with logic that we can figure out, like, what to logically prove. That's what I mean, to say that sets are equal. So all right, A is equal to B when this is true and this is true. Just like take their ideas, right, and AND them together. Now we've made the logical thing. Like, if you prove this, you've just proven that they're equal. Yeah. So A is equal to B. Say, like, this is X in A implies X in B, and X in B implies X in A. Those are just two sides of the same thing, so that's really a biconditional. So A is equal to B when, for all X, X is in A if and only if X is in B. That's pretty nice. Okay? So that's pretty cool. And it follows, like, this idea follows from less than and greater than. Like, X is equal to Y, right? when x is less than or equal to y and y is less than or equal to x. You see how that implies that they're equal? Same idea here with subsets. That intuition still works. Okay? So finally, I've given you so many things. You're going to have to go back to all these slides. I'm sorry. I'll just have them up for just a little bit, so you can go back and pause to what you need. But here are my questions for you now. You give this a try, please. So, all right. Here's some ideas. Let's define these sets. A is equal to this set, 1, 2, 3. And B is equal to this set. All the x's in Z, the integers, where x is an integer multiple of 42. So which things is it picking out? So what does B look like? See if you can figure that out. And then try to solve all these. All right, and I'll give you some hints as you unpause the video after you tried it. And then I'll do it too. All right. So A is pretty obvious what A is. What in the world does B mean? So B is like every integer. Like take all the integers and filter out only the ones that are integer multiples of 42. All right. So that's interesting. All right. So what does that look like? It's like every integer multiple of 42. So another way to read this is like, all right, it's equal to every integer multiple of 42, essentially, because like x is all the integers already anyway. So it looks kind of like this. Another way to write it is like 42 times x, where x is in Z. See how I'm reading that? So those are equivalent ideas if you think about it long enough. So it's like, it looks like 42 times some integer, like for every possible integer you could try. It's like, what does this set look like? It's got like, well, 0, because 0 is an integer multiple of 42 for sure, right? So you can just pick out 0 multiplied by 42. 42 times 1, of course. 42 times 2 is 84. And then all the negative numbers, right? Because negative integer multiples of 42 exist. Like you can take negative 1 multiplied by 42 and get like negative 42. Negative 84. And of course all the bigger and smaller ones of that too. Those are all in there. So, okay. Let's ask some questions about these things. So, all right, is 1 an element of A? Is 1 in A? Yeah, sure. We listed it with roster notation. Yes. The answer is yes. Is 5 in A? No, it's just got 1, 2, and 3. So that's not true. Is the set containing 42 and 84 only a subset of B? Absolutely. Like 42 and 84 are for sure in this set. They're integer multiples of 42. Yeah. Even though B is infinite, it's totally fine. This finite set is a subset of B. Totally okay. Is the set 1, 2, 3 a proper subset of A? It would be this, right? It would be this. They're equal. Those sets are equal. But it's not proper because this one is the same size. They are equal sets, and proper subset does not allow equality. You say no. But it is just a normal subset, if you want to think about it that way. And then finally, what's the cardinality of A? What is the size of A? It's got 3 elements, and so that's not too bad. The answer is 3 there. Okay. So hopefully that's making some sense. All the symbols are making sense in your mind. Do yell at me if you have any questions about this stuff. I know it's a lot, and so I don't have too many more slides. It's just mostly questions for you in the majority of the remaining slides. All right. Well, these guys. Is R a superset of Q? So another way to think about that is Q a subset of R? You just flip it around. That's totally fine. Another way of asking that is like, is Q a subset of R? Same question, right? It'll be the same question at that point. Let me draw my R, blackboard bold, all right? And then also, is Z plus, remember what that is? That's the set of all the, all the positive integers. Is that a subset of n, the natural numbers? Okay, so think about this, and then I'll show it to you, okay? So, okay, remember that R is all the real numbers, and Q is all the rational numbers. R is all the rational numbers, which implies it's all the elements of Q plus all the irrational numbers as well. And so yeah, is R a superset of Q? Equivalently, is Q a subset of R? Yeah, it's got all those elements. It's already in there, okay? So that's totally a true statement, okay? And then this one, is Z plus, is all the positive integers. The set looks like this, right? It starts at 1, 2, 3, on. Nothing smaller than 1, though. A subset of n, the natural numbers, which start at 0 in this class. 0, 1, 2, 3, ... Are all the elements in here also elements of here? Yeah, they totally are. There's also a 0, so n is strictly bigger. So it's also a proper. It's also a proper subset if you want to think about it that way. So yeah, this one's true as well. I hope you see that. Okay, a few more ideas. We're almost out of there. So let's make. You can do this. It's silly, but of course you can do it, right? You can put anything in a set, so obviously you can put sets in sets. All right, so let's talk about that. So like here's a set, call it A. A is equal to the set containing, right? Here's the outer parentheses or the outer braces for what the set A contains. A is, let's define it to be the set containing the set 1, 2, the empty set. The set can have the empty set, the set 1, 2, 3, and the set containing 1. So A is a set of sets. You see that? So here's what A looks like. Let me draw it. So here's A. It's a big blob. It has inside of it its own little sets. So A holds the set inside of it 1, 2. See this? So A holds the set 1, 2. A holds the empty set. A holds like a set containing nothing inside of it. A holds the set 1, 2, 3 inside of it. So it's a set of sets. And then what else? A holds the set containing just 1 as well. All right, so that's what A holds. Holds a bunch of sets. So this is going to be trippy. Do you notice? Do you see how the set 1, 2 is in fact an element of A? It's right there. It is an element. It's just one piece inside of A. It is an element at that point, even though it's a set. It's a little weird, I know, but that's a true statement. The empty set is also an element of A. It's right there. Got the empty set as an element of A. It was in the listed roster notation. 1, though, the number 1 by itself is not an element of A. You see that? Because in order for 1 to be an A, it would have had to look like this. Just 1 sitting out there as its own little thing. 1 is not an element of A. You see that? The set containing 1 is an element of A. This is true. The set containing 1 is in A. But 1, the number 1, is not equal to the set containing 1. You see that? Or just like this idea. The set containing 1. Those are not the same, right? Because that's like, you draw it like this, right? The number 1 just sitting out there is not the same as just a 1 by it in a set somewhere. You see that? Because this one just looks like a normal one, and this one, like, I draw it like that. You see that? That's the idea. And maybe I should just talk about it in drawing form. That's probably easier. 1 is not equal to the set containing 1. They're different ideas, okay? Interesting, okay? Very, very interesting. And so that leads us to the definition of what's called a power set. Some people say 2 words, some people make it all 1 word, but the power set of a set is something that you can compute from another set. A power set of a set A, for example, is a set of every subset of A, a set of all subsets of A. All the kinds of subsets you can write. You write it like this, P of A, with like an italic P kind of. But your book is lazy. It doesn't use italics, so it kind of looks like a predicate, but you can understand it from context. All right. So if A is the set containing 1, 2, and 3, those elements, then P of A, the power set of A, is this. What are all the subsets of 1, 2, 3? Well, you can pick out nothing. That's a subset. You can pick out individual elements. That's fine. You can make subsets containing just those things. You can pick out a couple things. Pick out the 1, 2, pick out the 2, 3, pick out the 1, 3. Those are all subsets of A. And then also just the whole thing, right? It's always a subset of itself. That's fine. Does that make sense? So those are all the subsets of A. The empty set's a thing, and the set itself is a thing because it's like subsets with the line at the bottom. It's not a proper subset, just a normal subset. All right. And then there's something special about like the number of these things. So A cardinality of A is 3. How many subsets of A are there? 1 empty set, 3 single size subsets, 3 single size or 3 size 2 subsets, and 1 size 3 subsets. So that's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 of them. Interesting. And this generalizes. This is a power of 2. That really does generalize. So if A, the size of A, is n, then the size of the power set, how many subsets of A are there? That's what it's asking, is 2 to the n, which makes sense because every power set, right? Every subset you're making, you got to try them all. You have 2 options for every piece. Like, all right, do you pick 1 or do you not pick 1? It's like you flip a coin. Do you pick 2 for your subset or do you not pick 2? You flip a coin. Two options. Do you pick 3 or do you not pick 3 for the subset you're currently making? You got 2 options again, flip a coin. So it's 2 times 2 times 2, 2 cubed. Does that make sense? So that's my hand wavy proof. For each element you have 2 options, either include it in your subset or don't, and you gotta try every piece, okay? So that's the idea there. And so, yeah, that's what's going on. And yeah, remember that this is not the number 1, this is the set containing 1. Set containing, which is a huge difference, right? This is the element 1. A subset, though, of A is the set containing the 1 element. Okay, here's a silly example from Twitter, just showing you that it's kind of the same idea, like 1 and the subset containing 1 is not the same. This time it's doing it with empty sets, all right? So this is saying the empty set is not the same as the set containing the empty set. Do you see? Like, the empty set is just like an empty thing of Tupperware, right? This is the empty set, and this is meant to be the set containing the empty set. Do you see how there's a difference? Because they're not the same. Still need the set itself, and then you can put an empty set inside of it. See that? So they're not the same. So A, if you define A to be the empty set, you can write it like this, right? Two parentheses, just close each other. You'd think I'd be really good at writing parentheses by now. I am not still. And then B, set containing the empty set. Not the same, right? You gotta write it like this. I guess technically you could write it like this too. It could be like set containing the empty set. Yeah, cool. But they're not the same. I hope you can kind of see why now. All right, questions with this in mind. Let X to be this. It's this weird looking set. Tell me what the cardinality of X is. Tell me if 2 is in it. Tell me if 2, 3 is a subset of X, and then is 5, 6, 7 an element of X. All right. And then also give these. What's the power set of the set 8, 9, 10? And then what's the power set of the empty set? So you're gonna have to do this one first, right? What's the power set of the empty set? And then what's the power set of that thing, that result? So it's a little complicated, all right? If it helps, you can draw X. So let me do it assuming you've tried it now. You can draw X. So X holds just 1. It holds the set 2, 3. It holds the number 4 just by itself. And it holds the set 5, 6, 7. So that's X. That's what it looks like. So what's the cardinality of X? Just like how many things are inside of it. You got 1, 2, 3, 4 things. You see that? You count the sets as just individual entities. There are 4 things in this set. All right. Is 2 an element of X? Is 2 just like floating around? No, it's absolutely not. It's part of a bigger set somewhere, but no. See how it's not an element? It would have had to been listed like this somewhere. 2 is not an element of X, though it's an element of one of X's elements. All right, what about this one? Is the set 2, 3 a subset of X? All right, you got to think closely about this. The answer is no. All right, do you see that? Do you see that the answer is no? Because that means, right? What is this doing? If this is a subset, this implies that 2 is an element of X and 3 is an element of X. That's what it means to be a subset. Implies that 2 is an element of X, 2 is an element of X, and 3 is an element of X. And that's just not true. There's one big set altogether, right? But what's true instead about the set 2, 3, and X? But the set 2, 3 is an element of X. You see that? That's the idea. That is true. And so, like, if you wanted to say this, to like imply this, 2, 3 being an element of X using the subset notation, you can turn it into something like this. The set containing the set 2, 3, that totally is a subset of X. All right, do you see that? This is also true. And it's honestly another way of writing this. 2 ideas. That's what's going on there. Okay, so hopefully you see the notation. It's very subtle, but now hopefully you can answer D correctly now too. Is 5, 6, 7 an element of X? Yes. It's all existing as one big chunk. All right, let's do power sets now. What's the power set of the set 8, 9, 10? So it's going to be very similar to this one. 1, 2, 3, just like going to substitute 8, 9, and 10. But this one's going to be hard, right? You can always check yourself. Like, what's going to be the size of the power set? It's going to be 2 2 to the 3, right? Because there's 3 elements here. So you can check yourself. There better be 8 things that I list. But all right, what's the power set of 8, 9, 10? What are all the subsets? Well, you can take nothing. The empty set's a subset. You can take just one thing. You take just the 8. You can take just the 9. You can take just the 10. Or you can take 2 things. You can start taking the 8 and the 9. You can take, let me write that better. Take the 8 and the 9. You could take the 9 and the 10. You could take the 8 and the 10. All right. The order does not matter for sets, by the way. I hope you've seen that. Should I be writing that somewhere? 10, 10, 10, objects or elements. Repetition doesn't matter. Also, order doesn't matter. Let me just write it here. Order doesn't matter either. I probably wrote that somewhere, but it's there too now. Okay, so I got that one, and then that's every size 2 subset, and then you also have 8, 9, 10. I think that's all 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that looks good. So that's every subset of 8. The set 8, 9, 10. This one's going to be a little tricky. So first of all, let's think about it. What is going to be the power set of the empty set? So you can do this. Like this holds true. It always holds true, even for empty sets. So if the cardinality of a set is n, then the size of the power set is 2 to the n. All right. So that implies, all right, whatever the power set of the empty set is, that implies, right? What's the size of the subset? Size of the power set, it's equal to the 2 to the power of the size of the empty set, which is equal to 2 to the 0. You see that? 2 to the 0, because the size of the empty set is 0. So that better be 1. So there's one thing inside of here, and it's the only thing you can think of, right? What's the power set of the empty set? Just like every subset. Every subset of the empty set, there's only one. It's right? There's only one thing that's a subset of the empty set. It's the empty set itself. Because this is true, right? The empty set is a subset of the empty set. That's a true thing. So that's how you do that. And then you're kind of off to the races, because now you can figure this out. What's the size of the power set of the empty set? Well, it is 2 to the power of 2 to the power of whatever the size of this guy was, which was 1. Right? There's one thing in here. And so that means there better be 2 things in the power set of the empty set. So, okay. What does that mean? Power set of the empty set. That's equal to the power set of this thing, because that was the answer for the power set of the empty set. The power set of this guy. And then, all right, what do? Well, the empty set is always a subset of everything, but do you see how this guy, the set containing the empty set, what do you know, is also an element? That's the whole set. The whole set is always a power set of itself. Or it always appears in the power set because it's always a subset of itself. A lot of words, but that's the idea. Those are 2 separate things, and those are living within the power set of the empty set. Okay? That's a very complicated question, but now you know the answer. Okay, so there's that one. And now, let us also talk about union and intersection. This is the last place I want to go today. It'll make sense, I promise. This is like Venn diagram kind of stuff. So, set union, little u for union. It's when you join 2 sets together into a bigger one. You're making a bigger set when you union together 2 sets. Okay? So, A union B is a bigger set. It's defined to be all the elements X, such that X was in A or X was in B. So it contains all the elements that are in either A or B or both. All right. So for example, if A is this and B is this, what is their union? If A is 1, 2, 3, and B is 2, 3, 4, their union is the whole thing. You see that? That's really not too bad. So their union is this guy. Oh, that's way too thick. Their union is all that. And so A union B in rainbow is equal to 1, 2, 3, 4. Okay? That's a bigger set. It's all the elements that are in either A or B. Next, we have set intersection. It's kind of the opposite. It's the other way. You just like flip the union sign around, do a 180. It's when you extract the common elements of the two sets. It's what they have in common. So A intersect B is all the elements X such that X was in A and it was in B too. All right, so it contains all the elements that are in both A and B. It's the shared stuff. All right, so if this is A and this is B again, can I easily copy and paste this? We'll find out right now. Can I delete the rainbow part? Yeah, cool. The intersection is the stuff they have in common. All right, so that's pretty clear from this diagram, right? What do they both share? What do they both have? This stuff. So that's going to be your intersection. A intersect B is equal to the set containing 2 and 3. Okay? So it's all the stuff that's in A and in B. And this is no coincidence. Notice the similarity between union and or and intersection and. Union is defined using or. See that? Intersection is defined using and. There's a very powerful similarity going on there, and it's going to help you remember this. Okay? So that's the idea. Here's one last question for you now. So remember the definition of union and intersection. Give this a try. Shouldn't be too horrible. Parentheses mean you got to do this one first, right? So let's do it. So what's A union B? Well, it's just all the elements that they share, and duplicates don't matter in union land, right? So you just write them once. So A is 1, 2, 3, B is 3, 4, 5, and so A union B is the set 1, 2, 3, 4, 5. That's all the elements they share. You don't count them twice. You don't duplicate them because it doesn't change the set. All right. What's the intersection? What's A intersect B? Well, what do they have in common? Well, 1 and 2 are not in B, 5 is and 4 are not in A, so it's 3. They have the 3 in common. So it's always a set when you do this. Intersection always creates a set, so it's just the set. What do they have in common? It's the set containing 3 as the intersection. Okay? And then what about this guy? A union B intersect C. Well, this implies we got to do B intersect C first. What is that? It's all the things that B and C have in common. And it looks like they've got a 4 in common and nothing else. So that's the set 4 that they hold in common. And then we're going to take whatever that is, take the set 4, and union it with the set A. So take all the things in A, add them to the things in B intersect C, and make one bigger set usually. So it's the 1, 2, 3 from A, and then the 4 from B intersect C. That's that's that final answer. That's the union between A and this guy. Okay? Hopefully that's making some sense. Do yell at me if you have any questions about this stuff. But that's our first taste of sets, and that's where I want to stop right now before your brain melts even more. And so we'll come back and we'll do some more next time.